Hello everyone, welcome to hydraulic modeling in MapleSim. So for those of you for who MapleSim is a bit of a newer tool or something that you haven't seen before, I will just go over kind of what is MapleSim used for. So we can use it for model creation with a CAD import tool, 3D visualization of system performance. We have tools that can be used for component sizing. A popular topic is motor sizing for, say, automation applications. We can do trade-off studies and optimization, integration with your tool chain, as well as motion profile generation for machines. So that's a very quick overview of some of the main topics that we can hit with MapleSim. But today we're going to be diving into some of the highlights of one of our libraries. So what's new in MapleSim 2019? So we have improved performance, even more connectivity, and increased modeling scope. So we're going to discuss briefly these three points, and then a bit more of an emphasis on increased modeling scope, which is where we have improvements into our hydraulics library. So in terms of improved performance, across the board, MapleSim is now faster when it comes to creating, simulating, and analyzing models. You can run simulations faster, and this is because MapleSim handles simulation constraints more efficiently, resulting in faster simulation code without loss of fidelity. We can have more efficient exported models, so the same simulation efficiencies that allow us to just run it quicker in MapleSim are also embedded into our exported models through FMI, Simulink, as well as our C code and other options. It's also more responsive to large models, so when you're dealing with a large number of components or parameters, model manipulation, so that's interacting with your model on the canvas and just trying to add components via the user interface, is going to be noticeably faster. In terms of more connectivity, MapleSim 2019 further enhances the extensive connectivity options for integrating MapleSim with the rest of your toolchain. So we have more simulation options when running imported models. One of the main ones is bringing in FMUs, or functional mockup units, can now run using MapleSim's variable step solvers in addition to the fixed step solvers. This means that you're not restricted to just using, say, an Euler fixed step solver. You can now take advantage of our variable step solvers and the simulation advantages that come with having variable step solvers. We have an updated FMI connector add-on for FMI 2.0 variable step co-simulation on export. So again, this is us just trying to stay on top of all the standards for FMI and FMU connectivity. And then we also have improved interactive analysis apps. So for example, our Monte Carlo analysis, the optimization, and the parameter sweep apps, you can now export your results to CSV files for use in Excel and other tools. So perhaps you want to export your data and send it off to someone else who maybe doesn't have MapleSim available to them. You can now send them the data as a CSV or as an Excel file. And then the focus of today's webinar is increased modeling scope. So there are new built-in and add-on components, and expanded support for external libraries means you can create more models faster. So the focus of today's webinar is the MapleSim Hydraulics Library, which has over 25 new components. Some of the more important changes are the directional control valve, so we've added a large number of these, as well as generic versions, so that'll give you complete flexibility if you're trying to have a very specific type of DCV. We've also updated some of the formulations. This is going to help with the speed of the simulations, as well as just numerical stability. Oftentimes when we're modeling hydraulic system, it's going to be a stiff model, and so we've made it so that you're not going to run into as many stability issues with our solvers. We've also updated our MapleSim electrical library, so we have new sensors and signals. We've also updated the MapleSim heat transfer library with 15 plus new components. These are components that allow you to have boundaries, visualization, which just makes your simulation a bit more intuitive, or it makes it easier to get your point across when you can see a visualization. That's really a big plus. We've also updated a lot of our Modelica support. So this is in terms of what you can bring into MapleSim from Modelica. So now we have the ability to import Spice3 library, the Modelica synchronous library, the Modelica multibody library, and the Modelica standard library 3.2.3. So again, just really trying to stay up to date on what is available in terms of the Modelica components, which means that you can always bring in any work you've done elsewhere into MapleSim and then continue your modeling. So this completes my kind of quick overview of what's new in MapleSim 2019. And now we're going to move on to some of the demonstrations. So what I want to do is just open up MapleSim, show a couple examples with these hydraulic components interacting with them, and also just showing some of the new features that we've also incorporated within the hydraulics library. So I'm just going to leave this presentation for now, and I'm going to go into MapleSim. So what you see here is an open session of MapleSim. In the middle is our canvas. This is where we're going to be building and designing our components, our models. On the left are the built-in libraries for MapleSim. The one we're going to be focusing on is our hydraulics library, which I will explore in just a little bit. On the right are the properties tabs. So whenever I click on a component, it's going to show me the properties I have available for me to edit or to change or to investigate. And all the examples that I'm going to be exploring today, for those of you who do have a copy of MapleSim or who do eventually get a copy of MapleSim, they're all available through our help section in our examples, physical domain, and hydraulics. So today I'm looking at the 2-input actuation, the directional control valve, and the hydraulic jack. So the first thing you'll notice if you're a user of MapleSim and you're coming from, say, 2018, or you've seen some videos of what we had previously in our hydraulics library, the first thing you'll notice is that we have a lot more different subsections, a lot more components as you start to expand these. Some of the big ones are in the restrictions. For example, before we only had this orifice. Now we can make the orifice area dependent on pressure, dependent on the flow. And what you can do is you can now have a lookup table that's just going to be able to look at some data that you might have and give you the area for your orifice accordingly. So this could be very useful, say you have some experimental data from a model that you've built and maybe you want to model it in MapleSim. Again, valves, we have multiple options and we've added quite a few components. For example, the pilot check valve, the shuttle valve, counterbalance valve. The shuttle valve is what I'll be focusing on in this example here. So what I've done to highlight the shuttle valve is I've connected it to 2 different signal pressure sources, each with these time varying signals. So the one on the left is going to be essentially a pulse going up and down between 0 and 1 10 to the power 6 pascals, and then on the right it's going to be just turning on to 2 10 to the power 6 pascals at 25 seconds. The shuttle valve, for those of you who are not familiar, essentially acts as an OR gate. So whichever of these pressures is higher, that's going to dictate where the flow can go through my component. What my shuttle valve is connected to is a hydraulic cylinder with a mass and spring damper. So as there is flow going into my hydraulic cylinder, my piston arm is going to be extending and there's going to be a resistive force from the spring which is going to want to push the cylinder back into essentially a resting position. I'll run a simulation just to show how quick a model like this can be simulated. So what you're seeing in the background is the system is taking all the equations from the components that I have here. It's looking at them using Maple to symbolically optimize and reduce the number of equations I need to solve, and then performing the integration. So we can see the total time for this simulation, if you added all of this up, is less than 6 or 7 seconds, so quite fast for a hydraulic system. A note that for the solver settings we are using Rosenbrock because this is a hydraulic system. We do want a stiff solver. So when I go into my results tab, I get some plots. These are generated because I have probes in my model, and what this allows me to see is the flow through the different ports in my shuttle valve. So this port A was the left side, port B was the right side, and port C is the port connected to my hydraulic cylinder. I can look at the orifice cross-sectional areas. So this one with the 1 index, this is for my port A, and the 2 index is my port B. The way the shuttle valve works is it essentially will go between 0 and whatever I've defined as my open area. So I've defined this value as being completely open. We see that as the A area is opening up, I'm getting flow through my component, and this is because I'm giving some kind of pressure into that left side. When the A side opens up, my B side closes, and for the first 25 seconds we see that it's just going from port A to port C, and it's pushing my cylinder. At 25 seconds, however, I am turning on, if we return to the model, this right side, which has a higher pressure. So now my shuttle valve is going to be letting the flow is going to be completely from the port B through port C. And so we see at 25 seconds, my flow is going exactly from port B and then through port C, no flow at port A. And because I'm just holding this constant, my cylinder is just going to continue to extend. So this is essentially just a very simple model just to show that we can now have the shuttle valve. You can see that I have a probe on here. So when I right click on components, I can attach a probe, and this is going to allow me to get information from the component. In this case, I've selected my volume flow rates, so just my flow at port A, B, and C, as well as my areas. And I can also probe other things. What I really want to highlight in this is the addition to our hydraulics library of these summary variables. So what I'm going to do is I'm going to add these summary variables to my probe list, and I'm going to run a simulation. Now, these summary variables, I can choose which units they're outputted in by looking at my hydraulic parameters. So what we've tried to do is make it a bit easier for the user to get results in units that will be more familiar to them, maybe make it a bit more easier to analyze the system. Because when you add a probe, you're always going to get the results in SI units. This means my areas will be in meters cubed, my flows will be in meters cubed per second, my pressure is going to be in pascals. But maybe that's not what I want. So by selecting these summary variables, I can choose the output that I want. So I can choose pascals if I want, or I can choose, say, PSI. And then for the flows, I can maybe say, I can leave it at liters per second. So if I run a simulation, excuse me, when I then go into my probe plots, so any probe that I add to the system is automatically added in my probe plots. Now I can look at my summary variables, and the units that I'm seeing here are going to be the units that I've selected in the hydraulic parameters. This summary variable is accessible through many of the components in the library, and it's just something we wanted to add in to make it a bit more of a user-friendly experience, something that will make it easier for users to kind of work with and then get some insight into the system. So I'm going to leave this example now, and I'm going to move on to our directional control valve. I'll open up the relevant section in my library on the left-hand side. So this directional control valve. So as you can see, we have a couple predefined three-state DCVs, as well as some two-state DCVs. The way that these are set up, and I'll zoom in just to make it a bit easier to see. So I have my DCV here. This is a DCV 4.3 close, and I've listed here or in the example, it lists what the inputs correspond, how the inputs correspond to states. So I have a signal input here. This is just a real signal. When my input is set to 1, then I'm going to have ports A and P connected, as well as B and T. That's what I'm seeing in this section of my diagram. So essentially these arrows, for those familiar with hydraulic diagrams, this will be natural. This is the natural way of displaying information for DCV. For those who maybe aren't familiar, these icons are just showing how your 4 ports, this A, B, T, and P, how they're going to be connected. So at input equals to 1, I have this configuration. When it's 0, I'm going to be closed because here I'm showing that nothing is connected. When my input is -1, I'm going to be in this state here where my P is connected to B as well as A is connected to T. If I click on the DCV, I could modify additional parameters, so my maximum area, so when it's completely open, what is the maximum orifice opening? The minimum orifice opening, so this is in real terms, you never have a completely closed valve. There's always going to be a little bit of leakage or some kind of very small area. This also helps with the simulation and makes it not so such a stiff system. So I define these parameters. You can also define flow discharge, Reynolds numbers, bands. All of this is explained in our help. If I open up the MapleSim help page, we do have one for the three-way as well as a two-way directional control valve. This will explain all the parameters, all the configurations, and really just kind of go over all the details. So if ever you're trying to work with the model, always explore the help sections. We always list the equations that are behind it. For example, most of these components use the similar formulation to the orifice. So if I follow the orifice formulation, it's showing me how my pressure change, or my difference in pressure, is related to my flow, and also just everything else that I would need to know from a mathematical point of view. So going back to my model, what I see here is I'm given a fixed pressure of 2,000 kilopascals. I have a signal that I've defined in my subsystem, and I'm connecting it to my DCV. What I'm doing is I'm going to actuate the system so that it's going to start in the first configuration and it's going to extend the piston arm. So I'm going to be in input 1, so the state where my flow can essentially go from B to T and then extend the cylinder arm. And then I'm going to actually change my state so that I'm then connected B to P, and that's going to actually push my, essentially retract my piston arm, push it back into it, closer to its original state. So I've already simulated this model, so I'm just going to open up the simulation results. So what we see here is exactly as expected. So here's our sequence. So this is the input we're giving into the component. I'm going from 1 to 0 to -1 and back to 0. So recall that when I'm in that 0 state, I actually have nothing connected. So there isn't really anything going on in the system. So I'm not expecting really any kind of flow or any kind of movement. So when I look at my cylinder stroke, I see for the first little bit, it's moving up. This is when I have my my switch sequence at 1. So it moves up and it's holding this position, and this is because I actually I have a maximum length that I'm allowing it to move. Then I leave it at 0, nothing changes. When I switch my input to -1, I see that my cylinder is going back. When it hits the 0 value, it's going to stop again because I've defined this total stroke length as 0.5 meters. And then it's just going to stay at this length until the end of the simulation. I've added probes to get my pressures and my flows at the different ports that I have, so that port 1 and port 2. And so this is essentially just running a very simple simulation with a built-in DCV. And here we can see that length that I was talking about, that predefined 0.5 meter length. This is because I've selected this use end cushions. The way the end cushions work is when I get to this defined length, there's essentially a spring damper that's acting as my contact. So I have a very high stiffness, very high damping, which means I'm just having a very solid contact. And it's really, there's not a lot of essentially rebound in this simulation. What I want to do now is just highlight the ability to, having this generic DCV, kind of just explaining how it could be set up. I think it's a very useful tool that we've added into our library. I'm going to go to my simulation results first because I want to just compare and show that the generic version can reproduce for results that you get with your original or with the built-in ones. So under my latest results, once they're selected, I'm going to right-click, select Save, and I'll just name these Original. So now I'm going to come here and I'm going to bring in my generic DCV, and I'm just going to make sure that I have the same maximum areas. So I'm just going to copy and paste this using Control-C, Control-V. I have the same minimum, and I have the same band, critical Reynolds number, and as well as the flow discharge. So these are the same. So I'm going to remove this component, and I'm just going to bring it over. I'm going to connect this in the same way. Add some probes. I'm going to give them the same name so that I can overlay the results easily. So I am just selecting this probe option up here. Name this one port 2. I'm going to run a simulation. By default, this DCV43 generic should be set up as a DCV43 close. So we see that, and you can't see the difference, and that's because I am getting the exact same results, but I have my red results for the original. The green results are the ones with the generic version, and we see that they match exactly. If I select this DCV again and I look at the parameters, the way that you can define essentially the flow between the different ports is through these 3 entry arrays. So when I'm looking at this first column, I'm essentially telling it how I'm allowing the different paths to be connected. So when I'm in state when my input is -1, I want B and P to be connected, as well as T and A, which is what I had here. When I'm looking at this middle column, or these second entries, this is my input 0, and so I see that I have it completely closed, so nothing is connected. When I look at the third column, I'm seeing that I have P and A, as well as T and B connected when my input is 1, which is what I had for the DCV43 close. So this shows how I can replicate it. I can then start playing around with, these scales. So right now, this 1 is multiplying my maximum area. So maybe I could always modify this and say, I want, when I have my input equal to 1, that this area from P to A is just half of this value, and maybe I want to make this slightly larger. This is how I'm scaling those areas. And if I run the simulation, I would expect some different behavior, because now my orifices, or my connections, have different sizes, so the flow and everything is going to be slightly different. Run. Alright, in this case it didn't seem to make much of a difference, but in general you would be able to go through, modify these values, run simulations, and kind of see how things are going to update and change. So the final example that I want to go over is this hydraulic jack. What I like about this example is that it really shows how we are a multi-domain tool. So MapleSim, you're not restricted to only be using a single domain. So for example, if you're building an electrical model, it doesn't only have to be electrical components. If you're building a hydraulics model, you don't only need to have hydraulic components. In this example, we see a lot of multi-body components. So the multi-body is essentially our kind of 3D mechanical. It's really one of the libraries we've put a lot of effort into in terms of a company and into MapleSim. So all of these components allow me to define things like fixed coordinate frames, rotational motion, some rigid bodies, and then I'm able to connect between this multi-body domain, this 1D translational, which are my green lines, and then into my hydraulics. So what I'm trying to model here, and there's a small schematic, is excuse me, I have a handle, it's attached to some rotating base, and as I move the arm up and down, I'm using this hydraulic system to actually have to push up some load. So in this case, and we've added some visualization, as I crank this arm, this silver piece is actually that load. It's moving up. This is essentially kind of looking at a hydraulic jack, say you're using for a car, or just any kind of simple system where you're just trying to lift something up just using manual force. And so it just really shows what you can do if you spend a lot of time and you put in the effort into your model. You can get this nice visualization. You can connect multiple domains together and really use the hydraulics library to its full potential. So I'm going to go back to my slideshows just for my final slide as I finish up this presentation. So what are some other ways that we can ensure success for you and our customers? So we have a lot of expertise and services here at Maplesoft. We can do digital twin creation with CAD import, as I mentioned earlier. We can do custom built apps for design, sales, and operations. So we do have some apps that are already added into the software. However, as a service that we provide is we can actually create some for you if you're in need of that. We can also do tools for component sizing. As I mentioned, we have some that can be used for, say, motor sizing or other types of sizing, but it can always be customized. You can always do design trade-off studies and optimization, digital twin interaction with automation software. So this is really going towards our connection with different partners such as B&R with our B&R connectivity tools, and also customized training courses and contract staff. So this is part of the engineering services. With the application engineering team, we work with customers who either are trying to work out a modeling issue or trying to build a digital version of their model. We can help with that, as well as provide training for Maple and MapleSim.